Well, thank you, Betty. Thank you, Susan. And thank you, MMSA, for providing me this opportunity today to talk to you about some of the research that we're doing at the National Minerals Information Center at the U.S. Geological Survey. My understanding is that we have a broad spectrum in terms of participants, from students all the way to CEOs. So I'm going to start off by giving a little bit of background just so that everybody is on the same page, and then we'll really delve more into the details. And I think we'll have plenty of time for questions towards the end. So I think I'd like to start by just, bringing the conversation back to, why are we all here? Why are we talking about this topic? And I think one of the major trends that has happened over the last couple of decades is that modern technology has moved really quickly, such that today, we're using pretty much the entire periodic table of elements. Even a single artifact like the cell phone contains, several dozen elements. Here's a figure from work that was done looking at, the elemental content of cell phones that was produced from 1998 to 2013. They didn't test for all elements, and it excludes the batteries, but you can see that there's already several, dozen elements that are used in the cell phones. And the other thing to note, and I think that we know this intuitively, is that technology is moving faster, right? So what this figure is showing is consumer electronics use in the United States on a per capita basis, looking at monochrome TVs back in the 1950s, to CRT TVs, to projection TVs, flat panels, desktop and portable computers, as well as mobile phones. And what this is showing are these S saturation curves. So you can see, the per capita use of monochrome TVs saturated at around half a TV per person. So, one TV for every two people. We're now, we're over one TV per person or so. The other thing to note about this figure is the shape of the curve, right? So not only are we saturating at a higher level, but we're getting there faster. And I think this is, again, something that we've known intuitively, but this is data to support that, the fact that, we're using, or we're demanding a lot more of these goods to satisfy our needs. And of course, this has important implication for mineral resource demand. And it's, of course, not just about consumer electronics, whether it's renewable energy technologies such as thin film, solar photovoltaics, offshore wind turbines, in healthcare, of course, that's a big topic these days, in defense and national security. And one of the biggest transitions that we're going through right now is the electrification of the transportation fleet. So these are just a few examples. They're by no means exhaustive, but it just shows the breadth of use of these often minor mineral commodities in technology that we require in everyday life. Now, to meet that demand, global production has had to increase, and it increased significantly, especially for some of the minor metals. So if we look at production here, I've scaled everything to 1 for year 1975. So production for bauxite has more than quadrupled, molybdenum almost quadrupled, zinc, twofold increase. And comparing that to world aggregated GDP, adjusting for inflation, it's also about 3.6-fold from what it was in 1975. So these commodities these large commodities markets are moving more or less at the same pace as global GDP, which would be as expected. Some of the minor metals, such as gallium, rhenium, and indium, are increasing several folds more. This is on a log scale. If it was on a regular plot, they would be off the chart. And so the demand for these minor metals has really exploded over the last couple of decades. And that's because the drive for these technologies are requiring these somewhat exotic elements of the periodic table to perform the function that is perfectly suited, whether we're going for smarter, faster, lighter, or smaller technologies. These are the minor metals that are able to perform that exact function. And the material scientists and engineers that are developing these technologies need these elements to do the job that they need. Now, I picked these commodities not at random. They're obviously byproducts. These minor metals are byproducts of the ones below it, more or less. Gallium is a byproduct of bauxite, indium as a byproduct of zinc, and rhenium as a byproduct of molybdenum as a byproduct of copper typically. And in fact, if you look across the periodic table, what you see is that a lot of the elements that are needed for these high-tech applications are often produced only or predominantly as byproducts. So you get the metalloids, whether it's tellurium, selenium, germanium, gallium, indium, some of the minor platinum group metals, the rare earths, zirconium, hafnium, vanadium, and of course cobalt, produced mainly as byproducts. That of course suggests that there might be some difficulties, maybe not, in terms of their elasticity of supply, so they might not necessarily follow demand signals. Another concern is that a lot of the production for these elements, sticking with the periodic table figure, are concentrated in a few countries, right? So you have the Democratic Republic of the Congo, which is a major producer for both cobalt and tantalum. You got South Africa, that's a major producer of the platinum group metals, as well as chromium, manganese, vanadium, zirconium. You got Canada and Australia that produce a little bit of everything. You got Chile, which is a major copper, moly, rhenium producer, as well as lithium and iodine. And then you have, China with pretty much everything else. So this concentration of production in one or a few countries is potentially problematic in terms of, thinking of it as putting all of your eggs in one basket. So you want to have a diversified supply chain if you're a consumer of these commodities, so that there's no single points of failure, so that you're able to have a stable supply chain. Now, digging a little bit more deeply into the Chinese production concentration, we see that this is somewhat of a recent trend, right? So the numbers that I've showed you were, I think, for 2015. This is showing a trend from 1996 to 2015 in this periodic table. So you can see, obviously, there's some commodities that the Chinese have had the largest share of global primary production for over this time period. So the lanthanides, the rare earths, yttrium, antimony, tungsten. China has been the major producer for these for longer than what this time frame is showing. But for some other commodities, it's relatively recent. So magnesium metal, gallium, germanium, cobalt refining, some of the other commodities, obviously a huge increase in raw steel production, aluminum, et cetera. So you can see these trending upwards commodities where China may not have been a major source or a major contributor to the global market, and now it is for a lot of these commodities. On the other hand, what we see in developed countries, including the United States, is that the US is becoming more and more import reliant. So this is something we put out in our annual publication, the Mineral Commodity Summaries. I'm showing the numbers from our latest one that came out, I believe, in February, a couple months ago. And we show, what is the US import reliance for the 90 or so commodities that we cover in our center. And the figure to the right is showing, what percent or the number of commodities that have at least 25% net import reliance for the United States. So the idea is that imports less exports relative to the consumption of the United States. So you can see in 1954, about 21 commodities increased to 46 commodities in 1984. And last year, we were up to 58 commodities. And you can see a lot of the growth there is for commodities that are over 50% net import reliance. So at least half of the US consumption is foreign sourced. Now, one thing we wanted to do is to realize that, yes, the US is import reliant, but even though that China has a lot of production, it doesn't have everything necessarily that it needs. So a couple of years ago, we did this study where we looked at US import reliance and juxtaposed it against Chinese net import reliance. And so things in the bottom left quadrant are things that are, both the US and China are not necessarily highly import reliant, so less than 50% net import reliant. And commodities that would fall in this quadrant include things like molybdenum, where it's in the far left corner, bottom left corner at 0,0, suggesting that both China and the US were net exporters of molybdenum. I believe these results are for circa 2014. In quadrant 2 are commodities for which the US is highly net import reliant, but China is not. So the rare earths obviously would fall under this category. Some of the minor metals that we mentioned before, indium, tellurium, yttrium, germanium, also highly import reliant for the United States. China is not. They're typically major producers of those commodities. The converse to quadrant 2, quadrant 3 are things where China is highly net import reliant, but the US is not. And so commodities that fall in this category include iron and copper mining. So the reason that you might think, well, China is actually a major producer of iron and copper. Well, they are, but their consumption is higher than their production, so they are actually a net importer for those commodities. Now, I did neglect to mention the color scale on here. It's based on the Herfindahl-Hirschman index for production concentration. So the warmer the color, the oranges and the reds, the fewer the number of producers there are globally. So you can see in quadrant 3, beryllium is really the only one that's in the warmer colors. That's because the US is the major producer of beryllium due to a concerted effort, right? Due to Department of Defense Title III program that has sustained and helped out to the beryllium industry at least get started. When you contrast that to quadrant 3, there are obviously a lot more warmer colors, suggesting that China is typically the dominant and producer for those commodities. Quadrant 4 is perhaps the most interesting quadrant. These are commodities for which both China and the United States are highly import reliant. Really no surprises there. The platinum group metals, lithium, titanium, manganese, tantalum, chromium, and in the far right, upper right quadrant, niobium, where Brazil is obviously the major producer for niobium. So these are the commodities that you would expect that given that neither the US nor China have sufficient supplies for, they're both potentially going to be competing on the global stage to make sure that they have access to those supplies. Now, of course, the Chinese are not sitting idly by. Through foreign investments, China has been able to go out and secure a sizable portion of the supplies that they need for things like cobalt, especially in the DRC, Zambia, and Papua New Guinea, as well as other commodities, including niobium in Brazil, lithium in Australia and Chile. And so this is obviously a strategic effort on their part to make sure that their manufacturing sector has the commodities that they need, given the fact that they don't necessarily have at least sufficient supplies domestically to satisfy their needs. This may also, in a conflict scenario, potentially limit the supply that the US might have access to. Now, so you might ask, well, what is the US government doing about this? So within the US National Science and Technology Council, which is part of the Executive Office of the President, there's a subcommittee on critical and strategic mineral supply chains, of which the Department of Interior, which the USGS sits under, as well as the Department of Energy, is our co-chairs with the Office of Science Technology Policy. There are members from all the major federal agencies within the US government. And the subcommittee has several functions, one of which is to develop, apply, and periodically update a methodology to dynamically assess mineral criticality for commodities that are important to the US economy and national security. So what I'll do is spend the rest of the time really talking about this methodology and its results, and then follow up with a couple of examples of, well, now that you know which are critical, what can be done about it. So in our latest iteration of how do we assess which commodities are most critical, this is a paper that we published in February of this year. We really stepped back and said, okay, let's look at what the traditional definition of risk is. And for our purposes, we're talking about a supply risk. So a risk associated with a supply disruption. So typically when you have a risk, it's assumed to be proportional to a hazard, which is a likelihood of a supply disruption. You have to be exposed to that hazard, and you have to be vulnerable to it. So are you able or not able to withstand the effects of a supply disruption? So that's the general framework that we were thinking of in terms of how do we assess which commodities are most critical to the US. And so under that, realizing that we had to balance both, analytical rigor with data availability, we ended up using a methodology that sort of balances those issues. So one thing to note here is that if you think about risk in these three components, um, any one of these or all three of these are necessary for there to be risk. And if you remove any one of them, then the risk goes away. So if you're no longer exposed or if you are no longer vulnerable, then the overall risk would diminish, even if the hazard might still be high. And so that's important to think about, and I'll get to that a little bit later. So using this general framework, what we did was we came up with a set of indicators to help us understand and quantify really what the supply risk is for the different commodities. So we have our three sort of categories. So there's a disruption potential, that's our hazard. There's trade exposure, that's our exposure, and economic vulnerability for our third component. And so the issues are, there's a likelihood of a supply disruption, there's a degree of exposure to that supply disruption, and is there an ability to withstand that supply disruption? And so for the first component, we said, okay, if the production is concentrated in countries that may become unable or unwilling to supply to the United States, then the likelihood of the supply disruption is higher. So we looked at, again, production concentration. So are there a lot of producers, or is it really dominated by one country? And then we weighted that by whether or not those countries we felt were willing and able to continue to supply to the United States. So to apply an ability metric, we use the annual survey of mining companies done by the Fraser Institute. I would imagine that a lot of the participants on this call are familiar with this survey because you're probably being asked. It's a survey to mining and exploration executives to talk about something on the order of like a dozen or so policy factors, including availability of labor, political stability in the country, uncertainties regarding regulations, taxation, the quality of the geological database, to tell us whether or not this country is an attractive jurisdiction for companies to continue operating in. And so we use that as a proxy for judging whether or not a country might be able to continue to supply the United States. So the idea there is that countries that would have a low rating here, colored in the reddish colors, because they either have relatively unstable governments or political instability, or there might be situations where it's an unfriendly climate for continuing to operate mining operations or processing operations. So countries that show up relatively well here are the Northern Scandinavian countries, Canada, Australia, et cetera. Some of the countries that don't do very well here include Afghanistan, Venezuela, Sudan, et cetera. For willingness to supply, we came up with our own indicator. And here the idea was if there's a stronger tie with the United States, and by ties we looked at trade ties. So if there's a strong, if a large percentage of, what we did was we calculated the amount of trade, the bilateral trade between that country and the United States. If that was high relative to that country's GDP, we said there's strong trade ties. If there are shared values, so if it's a country that had similar values as the United States, we use the Freedom House indicators for that. So looking at democratic countries, open press, freedom of the press, freedom of religion, et cetera, to say these are countries that share the same values, so they're less likely to intentionally cut off the United States because of that bond. And also looked at military cooperation. Are they an allied country or not? So countries that obviously do really well here are, OECD countries, Western Europe, South Korea, Japan, Australia, the Latin American countries, South Africa. Countries that perform relatively poorly here, Iran, Syria, Cuba, Somalia, Sudan. China comes out somewhat as a middle tier on this scale, because you can imagine we may not have a lot of shared values, but there's strong trade relationships there. And so that actually, I think, makes sense in terms of, yes, there's been a lot of tug of war in terms of the trade issues, but so far we haven't really cut each other off because we realize how strong of how important trade is between the two countries. On the exposure front, the trade exposure component, here we used a familiar metric, the net import reliance, which I showed before. Really, we're looking at imports minus exports relative to the apparent consumption, where apparent consumption is calculated as primary plus secondary production plus net imports plus any stock releases minus additions. On the economic vulnerability front, this was probably where we spent a lot of our time and probably the hardest to quantify. What we ended up doing was looking at the annual expenditure on a specific mineral commodity by an industry within the manufacturing sector relative to that industry's profitability, right? So the idea there is that if a specific industry has to spend a lot of money, there's a large expenditure on a specific commodity, and their profit margins are relatively thin, then any of the actions that they might be able to take would be diminished, right? So there are various actions that a manufacturing industry or a manufacturing company might be able to take. They might be able to absorb the price increase due to a supply disruption. They might want to pass that price increase on to their customers, maybe for the short term. They might want to substitute it out with a different material. They might want to use their strategic inventories. Under any of these possible actions, we felt that it'll be difficult to ascertain exactly what one company might do. But in general, if they're not spending a lot on that commodity and their profit margins are relatively healthy, then their ability to perform or to undertake any of those actions is probably greater, all else being equal, than a company or an industry that has thinner margins and has to expend a lot. So to do that, how did we do that in practice? So here's one commodity, platinum. We know its uses, what their uses are. So it's used in automotive catalytic converters. It's used in reforming catalysts for the petroleum industry. It's used in a variety of chemical catalysts, for example, in nitric acid manufacturing. It's used in hard disk drives as well as thermocouples. It's used in glass manufacturing equipment. It's used in medical equipment such as pacemakers, in anti-cancer drugs, and a little bit in dental. And of course, it's used in jewelry and investment vehicle. So what we did was we tied those uses to specific NAICS codes. So NAICS is the North American Industry Classification System. And so there are so within the manufacturing sector, there are there are nested tables where, a larger a number with more digits means a finer disaggregation of a specific industry. So for example, industry 334112 is the computer storage devices. So the hard disk drive manufacturers would fall under that category. So what we did was we linked data that we had regarding consumption of that commodity by these uses to a specific NAICS industry using data from the US Census Bureau in the economic census that they put out every 5 years, and then the annual survey of manufacturers that they put out in the intermediate years, to tie it regarding their profitability for that specific industry. So let me give you a more detailed example of how this metric would work. I promise this is the last equation I'll have on here. But what I'm going to show is that there are two components to this. There is the part to the right, the expenditure, EXP, of a commodity I in industry J in year T relative to that industry's operating profit for that year. So that metric is saying, expenditure relative to operating profit. And then we also want to weigh it by, well, how important is that industry to the overall US economy? So there we look at the value add, so the contribution to GDP of that industry relative to the entire GDP of the United States, to give it a sort of weighting. And what I'll plot here is this, the latter component will be on the horizontal scale, and the vertical component will be this expenditure to operating profit ratio. And then the overall area, because we're going to multiply the two, tells you about the contribution of a specific use to this vulnerability score. So here's an example for aluminum. So so there are something on the order of, I don't know if it's 20 or so uses of aluminum. This, I think, is for year 2008, but we've done this for about a decade. So what it's shown here is on the horizontal axis is sort of the contribution to US GDP by the industries that these applications are used in. So the wider this bar, the larger the contribution of that industry is to the US economy. So you can see a couple of the white bars, passenger cars and light trucks. So no surprise there. that's a really important industry to the U.S. economy. And actually, if you sum all these up, it sums to a little over 6% of U.S. GDP for this year, almost $900 billion of value add. So a significant contribution to the U.S. economy just by these users of aluminum, right? On the vertical axis, the taller the bar, the more vulnerable that industry would be to aluminum price shocks for that year. So they would have a larger expenditure and a lower operating profit. So, for example, metal cans actually comes out on top. No surprise there. They're highly dependent on aluminum, right? So metal cans and semi-rigid food containers, they really are dependent on price fluctuations for aluminum, so they have a relatively high tall bar. It's a relatively skinny bar because their contribution to U.S. economy is actually relatively small. But the overall area of the metal cans box versus the passenger box is actually about the same. So they have it for different reasons. One is they're more vulnerable. The other is they're more important, and they come out to be about the same. So that's sort of how you can gauge this. And if we want to get the score for aluminum overall, we would sum the area underneath this curve to get a complete score for aluminum for this specific year. Okay, so those are the three components. So let me talk about a little bit about the results look like. So this is for year 2016. The disruption potential, so the likelihood of a foreign disruption, is plotted on the horizontal axis. We simplified everything on a 0 to 1 scale. We normalized everything for all three indicators, as well as the overall supply risk. So the distribution potential is on the horizontal, the economic vulnerability is on the vertical. The point size that I'll be showing is the trade exposure, so the net import reliance relative to apparent consumption. And then the overall shade of the point will be the aggregate supply risk score, which is simply the geometric mean of the three indicators. Okay, so I'll show these in different clusters so it's a little bit easier to read. So again, in the bottom left quadrant, you have things that have low supply disruption, low economic vulnerability. So things that come up here include cadmium, arsenic, tellurium, strontium, selenium, mica, etc. Folks might be surprised to see lithium on here. In general, there's obviously a lot of production of lithium globally, especially in the last couple of years, with Australia ramping up production. The US, at least in the recent past, 2016, was not necessarily a large producer of lithium-ion batteries. This, of course, might change. So it'll be important to see how this changes in the future. You will notice, however, the size of the dot for all of these, except for cadmium, is relatively large, suggesting that, yes, there is a relatively high trade exposure for some of these commodities. Commodities that are in the top left quadrant, so really high economic vulnerability but relatively low disruption potential, include things like copper, gold, iron ore, lead, phosphate, and molybdenum. The commodities that are in blue are and have the smallest dot are there because we're typically a net exporter of them. So molybdenum, gold, iron ore, we're a net exporter of them. Really important to the U.S. economy, but typically we're self-sufficient in terms of the U.S. economy, so less of a concern there. In the same quadrant, but higher trade exposure, are things that include, nickel, manganese, some of the platinum group metals, chromium, tin, niobium, antimony, germanium. Aluminum is up there, obviously really important to the U.S. economy, as I was showing. It's up there because we obviously have no really bauxite production, except for minor production that's not really for metallurgical use. So it's there. We look at it from a supply chain bottleneck perspective. So if any point of the supply chain there is a high score, that's a score that we use. Moving on, we have some commodities that are maybe higher in the supply disruption potential, but relatively low in the trade exposure. So beryllium and helium, obviously the U.S. is the largest producer of both of those commodities, so they turn up relatively low there. Tungsten and magnesium. Actually, tungsten, most of our production, or maybe all of our production in the United States is secondary, so that would be even higher if we didn't have any of the recycling going on, typically in terms of tungsten carbide being recycled, but perhaps other uses as well. And finally, furthest to the right, we have our rare earth elements and some of the minor metals, some of the minor PGMs, iridium, ruthenium, gallium would also fall on here. So you'll see a general trend from a top left to a bottom right, which I think makes sense, right? So you have things that humanity's used for millennia since the antiquities, such as gold, that really important to the U.S. economy, iron ore, but it's widely distributed throughout the globe in terms of production. There's a relatively low risk of a supply disruption, where things that maybe have niche applications are typically produced perhaps in a few countries, and typically that country is not the US, and so they have a relatively high supply disruption potential and a relatively high trade exposure. Okay, so that was for year 2016, but as I mentioned before, we did it over a period of a decade. So I just wanted to show you how some of the results changed over the decade. And so I picked lanthanum as an example from the rare earths. So, we started year 2007 with the analysis. We see that, high disruption potential, relatively moderate to somewhat low economic vulnerability and high trade exposure. It actually moved a little bit to the left and then ultimately moved up, with a price spike due to China's threat to cut off supplies, drove the global prices of rare earth to unprecedented levels. So we saw that the economic vulnerability went up because all of a sudden manufacturers had to pay a much higher price for the rare earths in general. Eventually, the prices did come down. However, there was concentration of production even further due to a large amount of illegal production in China that was going on there. So it moved it even further in terms of production concentration and disruption potential. Eventually, it's been moving back as production outside of China, mainly outside in Australia, but also elsewhere in the world, the production has ramped up. So the disruption potential has thus decreased. And so what we've done is sort of done almost a full circle, and we're sort of back to where we were in around 2007, 2008 timeframe. And I would imagine we're updating the data now to 2018. I imagine we're sort of back on the cycle again, and we're potentially repeating this cycle. And I think one of the goals with the federal strategy that I'll talk about in a minute is how do we sort of break the cycle so we're not continuously going back and facing the same issue again, and how do we have a resilient and low risk supply chain for not just the rare earths, but for some of the other commodities as well. Okay, so that was for lanthanum. These are the results for all the commodities that we covered, 52 commodities in all. This is probably too small to see, so let me zoom in a little bit. So what I've done here is I've ranked ordered them by their average score for the decade from 2007 to 2016, assuming there are scores. For some of the commodities, you can see some of the rare earths that are used in magnets. We didn't have data prior to 2015 because the trade code for the permanent magnets that are consumed in the United States wasn't disaggregated enough for us to look at it prior to mid-2014. So we really couldn't get a score for 2014. So we really started in 2015. These are the top 23 or so commodities based on this averaging of the scores across the decade. I've also noted here the leading producers. So no surprises there. China is, the dominant producer for most of these commodities. Otherwise, it's DRC or Rwanda, South Africa, Brazil, or Russia. Actually, for cobalt, as I think most folks know, DRC might be the largest miner, but China is also the largest refiner for cobalt. So actually, it would win there as well. One thing this analysis also allows us to do is look at which application is really driving the vulnerability score. So you can see for dysprosium, obviously, no surprise, it's the permanent magnets. For yttrium, it's the advanced ceramics. So this is the thermal barrier coating that goes on to those ceramics for jet aircraft. Neodymium again. For cobalt, again, in the United States, we're not yet or haven't been a major lithium ion battery producer. So for cobalt, the majority of the use for cobalt is actually in superalloys. And some of the other ones, lanthanum, cerium, and catalyst. So this allows us to see, what is the application that's really driving the vulnerability, and what portion of that vulnerability score is really being driven by one use versus many uses. So you can see for aluminum, for example, the passenger cars and light trucks, is the largest contributing application, but it doesn't contribute, it only contributes a portion of that vulnerability score because aluminum has a lot of other uses as well. Some of the work that we're currently undertaking is really delving into this vulnerability score a little bit more, trying to understand how the vulnerability might ripple through the US economy and ultimately affect US GDP. So we're hoping to be able to use economic input output tables to try to drive at that information and be able to not just provide an indicator, but an actual impact in terms of dollars. What is the estimated impact to US GDP due to, we can plug any number of scenarios and see what that might look like. So that's work that's ongoing right now. Invite me back in a year or so, and hopefully I can share with you some of those results. Okay. Another thing that we were working on recently, and this was a study that we published in 2019, is looking at earthquake hazards, right? So what I've talked about so far in terms of the hazard model is really about man-made hazards, right? So disruptions due to countries that may become unwilling or unable to supply to the United States. But of course, in addition to man-made hazards, there are natural hazards that can affect supplies. And being the US Geological Survey, what we decided to do is talk to our earthquake colleagues and say, could we get an estimate for what earthquakes might do in terms of disrupting? In this case, we decided for obvious reasons to pick copper. And so we did the study published in 2019 looking at South America, mine production as well as smelter and refining production. And I think if I remember correctly, the estimates were somewhere between 2 and 5%, depending on your vulnerability model, 2 to 5% of annual South American copper production may be disrupted in any given year due to earthquakes. So it's an interesting result, and we're expanding that study to a global basis. So hopefully we'll have these results published in the next couple of months, probably early 2021. We'll be able to see it for copper globally. We also went ahead and added Rhenium because we thought that would be interesting to look at Rhenium given its concentration of production in a few locations. But ultimately what I hope to do in our group is to expand it to as many commodities as we can, and then not just look at earthquakes, but potentially look at other natural hazards as well. Okay, so that gives you a little bit of flavor about some of the work that we're planning to do to continue to expand and refine the analytical work on assessing supply risk. One thing that I'd like to turn to now is the federal strategy. I mentioned this before. I think a lot of you probably have heard of this, but there was an executive order that was put out and through the subcommittee that I mentioned, the Critical Minerals Subcommittee, there's been a strategy that's been put out by the Department of Commerce that outlines 6 calls to action for which, to help reduce this supply risk and the U.S. Risk for these commodities. And so I'll just enumerate them now. So call to action 1 is really about R&D, so research and development and deployment across the supply chain. This is led by Department of Energy as well as others to look at alternative materials, to look at recycling technologies, etc. Call to action 2 is really led by Department of Defense, also supported by Department of Energy and others. And it's looking at the defense industrial base and the mineral supply chains there. So you probably have seen the request for proposals that have been put out, as well as several presidential determinations that have been put out there. And the focus so far obviously has been, for obvious reasons, on the rare supply chains. Call to action 3 is enhancing international trade and cooperation, led by our friends in Department of State and Department of Commerce. We at USGS are also involved in these discussions with our counterparts. A lot of discussions going on there, obviously, with our friends and neighbors, Canada and Australia. That work obviously is ongoing, and there are various efforts on that front. And I would defer you to Department of State to get a status on that. Department of Interior, where USGS sits, is really focused is really focused on call to action 4. This includes improving our understanding of domestic critical mineral resources. It includes the work that I just showed you in terms of updating and refining the methodology for the critical minerals list. It also includes a lot of other initiatives. So there's a large initiative which I would imagine folks have heard of at the USGS that's in collaboration with the state geological surveys called Earth MRI, the Mapping Resources Initiative, where it's looking at improving the mapping in terms of geophysical mapping, topographic mapping, as well as geological mapping of the United States. Again, in collaboration with the state geological surveys, that work is obviously ongoing as well. Call to action 4 is about improving access on federal lands and permitting issues. So that really falls on the land management agencies, the Bureau of Land Management and the Forest Service under Department of Agriculture. And finally, call to action 6 is about growing the workforce. So realizing that, if you look at the number of degrees that are being handed out in geology, economic geology, in mining engineering, it's not where it needs to be. Understanding, that the workforce needs to grow. This is being led by Department of Education as well as NSF to try to help that initiative grow and continue. Okay, so these are the 6 initiatives. I'd like to take one step further and give a couple of case studies with, well, how do we actually tackle and actually reduce the supply risk for any individual commodity? So the way at least I think about it is that we can potentially use scenarios to help us determine which of these strategies can help us achieve our goal. So let's take an illustrative goal of saying, let's reduce our net import reliance to no more than 25% from non-allied nations, if that's our stated goal. Again, USGS doesn't set policy, doesn't set regulation, but let's assume that this is a stated goal. So how would we go about figuring out whether we can even get there? So the way I would think about it is, okay, so in general, historically, domestic demand has been increasing, domestic supply has been decreasing. The difference between those two would be our current net import reliance. So these are just some illustrative numbers for conversation's sake. Let's assume business as usual scenario, demand continues to increase, supply flattens out or decreases. How would we get to our stated goal if that's our stated goal? And again, harkening back to the original supply risk framework, we can either decrease the hazard, we can decrease the exposure, or we can decrease the vulnerability. And here, and if you tackle any one of those 3, then you decrease the risk overall. And so here I'm just suggesting that, okay, let's tackle the exposure piece. And if we reduce that, then the overall risk would decrease. So there are various strategies, right? So you can potentially improve manufacturing. So, near net shape manufacturing, 3D printing, et cetera, might bias a little bit. You can potentially find substitute or alternative materials. That's something obviously that companies would want to go towards, assuming that we're not going to get a decreased performance. There typically is a decrease of performance and typically a higher cost, or there might be some challenges there, but it's an option. Potentially, you can also work through with allies to secure those trade relations. Of course, on the domestic side, we can increase primary production. We can increase secondary production through enhanced recycling. And so we have our, the projected net import reliance. And if it's down to 25%, great. Maybe the rest of it, we can use the national defense stockpile to sort of buffer against any supply disruption that might happen. So this is sort of a generic way that I'm thinking about in terms of these wedges. It's a concept that I didn't come up with. It's popularized in other sciences. But the idea there is that, if there are these strategies, which one is really going to be the most effective for which commodity, and how fast can it get us there, and how big could that wedge be? So a couple of illustrative examples to that effect. These are not necessarily finished works, but just to get you thinking about the way we're thinking about it. The first thing we need to do is really look at what the demand numbers might look like in the future. So one of the bigger transitions that's obviously going on is the transition to renewable energy technologies, right? So this is information from the US Energy Information Agency from 2019, looking at world electricity generation capacity projections up to 2050 globally, right? So these are global numbers. And what you can see here is that, coal is expected to flatten out and maybe decrease a little bit. Hydro is also the same, nuclear, other renewables, and liquid-fired fossil fuels as well. The things that are expected to increase are natural gas, wind, and solar, right? To a fact that they expect solar to be the largest single source of electricity generation capacity. It's important to realize that this is capacity, which is important from the perspective of demand for commodities. And actually all three of those, right? So solar, obviously, we'll talk about it in a second, would require metals for that. Natural gas, if you're using turbine blades, you're going to require metals for that. Wind turbines, obviously, you're going to require mineral commodities for that, including if it's offshore, you're going to require some of those rare earth permanent magnets. But let's focus in on some of the solar photovoltaics. As folks may know, there are at least 4 commercially available solar PV technologies, the most dominant of which is the crystalline silicon. It requires silver. The amount of silver has actually been decreasing rapidly, but it still does. Cadmium telluride is another one. It's a thin film. It requires cadmium and tellurium. SIGs requires copper, indium, gallium, selenium, and in some cases, the amorphous silicon requires some germanium. Although I think that's actually not really in the picture anymore. So you can see a lot of these, technologies require these minor metals, and they're minor metals and also byproducts, right? And so if we think about for the United States, this is a map of where these solar, these are utility scale solar photovoltaics are distributed by type. You see that the largest, of course, are the crystalline silicon, the most dominant type. It is the most dominant type for the world as well. The second largest is the cadmium telluride. So that's the second largest contributor and the largest source for the thin film solar photovoltaics. Cadmium, I think, is not really a concern. Tellurium potentially is a supply bottleneck. So we have a follow-up study on this looking at, well, how much tellurium could potentially be recovered from copper anode slime. So obviously tellurium is mainly produced as a byproduct from copper refining. It gets deposited in the copper anode slimes. Some companies do recover it. Most companies probably do not, and that's what we're trying to figure out. How much more tellurium could be recovered in terms of just quantities, what is out there that is currently being discarded. So tellurium production is on the order of between 400 and 600 metric tons a year, pretty small market. Most copper refineries couldn't care less, right? It's such a small rounding error, they wouldn't want to mess with their process. But maybe if the price was right, and if it doesn't affect their recovery of other things, such as gold, maybe they'll start to go after it. So we have a working group right now, including folks from Missouri University of Science and Technology. They have an excellent survey of global electrolytic refineries to try to understand what is in the slimes, to be able to at least give us a ballpark estimate for, how much is there? Could it satisfy demand if the market was there for cadmium telluride to become a larger share of global, or at least US solar PV production. So that work is ongoing, and we'll be happy to share it with you once it's ready. Another commodity that we've been looking at for the last couple of years is tantalum. And so as folks may know, tantalum has had a lot of changes in both its supply and demand. It used to be mainly produced from tin slags back in the 1970s, and then it shifted to being produced mainly from mineral concentrates in Australia, to then being shifted to being mainly produced in the DRC and Rwanda. And now we're actually going through another shift where it's being produced as, again, a byproduct of lithium in Western Australia. So a lot of shifts in its supply. On its demand side, it's also had a lot of shifts where it typically was used, and still obviously is used in capacitors. I'm sorry, the slide looks like it's cut out, but that light blue color is capacitors. That's still its biggest use. But another, several major uses in the yellowish tones in the chemicals, with alloys, additives, and sputtering targets have become a more dominant use as well. So the questions that we had are, how are these shifts affecting the tantalum's global stocks and flows? How much tantalum is used, recycled, and lost at each life cycle stage? How much tantalum is still in use today, and how much can be discarded? How much is being discarded annually? And the questions there are, as you can imagine, that geologically we don't necessarily have a lot of tantalum readily available, and probably won't in the United States. So, but we are importing a lot of tantalum in terms of finished goods into the United States, as well as raw materials. So we wanted to understand, well, what is potentially available, because maybe the lever to pull here and the strategy that might be most effective is to increase recycling to solve this issue. So our first study was looking at the global flows. And so what it's showing here in a Sankey format, so the width are proportional to the quantities. These are all in metric tons of contained tantalum, regardless of the process flow. So starting from left to right, in 2015, so you see Rwanda and the DRC are the major suppliers as in terms of primary production. Those then go to processors, manufacturing, use, and end of life. And the flows that you see at the bottom are the recycling flows, whether it's internal scrap, new scrap, prompt scrap, or old scrap. And there's also a significant amount that gets discarded or not necessarily entering the recycling chain at the end of life. So this is for 1 year, 2015, but we can look at it over time, and we did. So you can see this pattern from 1985, where the majority of tantalum came from tin slags, to 2005, where Australia was the largest producer, to 2015, where the Great Lakes region in Africa was the largest producer. And then we're able to see how the flows are changing in terms of not just production, but also consumption. And we're able to come up with metrics, including this one on end-of-life recycling rate. So this would be, what percentage of what comes out of use actually ends up getting recycled. And what we can see here is that based on our estimates, it might have topped out at around 25% end-of-life recycling rate, and has since decreased to around 18% or so. These numbers are actually, I think, relatively accurate because they've been independently verified by other studies that were done. So we're recycling about 18% of tantalum at the end of life. So that's important. It's a different metric than if you're looking at it as new scrap and old scrap. This is simply end-of-life recycling rate. So it actually seems relatively low, but for most commodities, that's actually pretty high, unless you're talking about things that are really well recycled, like aluminum and copper and the precious metals. 18 is actually pretty good in terms of some of the minor metals. Of course, we can do a lot better. But the question is, why did we decrease, right? So why is the recycling rate going in the wrong direction? And based on our best estimates, it's decreasing not because of anything that any one company is doing, but simply the shift that we talked about at the beginning, where it was mainly used, obviously still using capacitors, but there's been a shift from its use in carbides and maybe heat exchangers, so milled products, to being used a lot more in electronics. So those sputtering targets, as well as some of those tantalum chemicals, really end up getting used in electronics. And electronics obviously are notoriously difficult to recycle, mainly because of its lack of collection. Even when you do collect it, you still have some technical issues, obviously, that you need to resolve. And oftentimes it's simply not economic. They'll typically go after the copper and gold and then the other precious metals that are there, and may or may not recover some of these minor metals that might be in there. Again, when we talked about, if you have a cell phone and you got a circuit board in there, and you're holding several dozen elements in that circuit board, there are companies that can recover these elements, but if it ends up in some of these recycling chains where it might be sent off to a less developed country, they might be going after the gold. They might not be getting much of the gold, and they might be actually doing some harm to themselves due to health hazards in terms of the way they process them in the backyard or whatever. So that's a challenge in terms of recycling, being able to solve this problem in terms of closing the loop here. So just continuing on this theme of tantalum in terms of what the numbers actually look like, well, we can look at it in terms of, stocks of use above ground, right? So just as we think about geological resources reserves, we think about stocks of tantalum above ground. So we've mined something on the order of a little bit more than 50,000 metric tons of tantalum since 1970. Some of it's been lost in processing. Some of it might be somewhere in industry stocks. You subtract those two, our demand net of recycling is that quantity. You can see most of it, more than half of it, is in capacitors. Some of that demand has been lost to manufacturing in manufacturing process. Some of it's in use dissipation. This is some of the carbides that have had obviously wear and tear, so you lose a little bit of that. There's some downcycling, so downgraded scraps. So a lot of those super alloys, they might not go to the right recycling stream. They might be downgraded to a different kind of steel. So you lose the property of the tantalum. But a lot of the losses are those end-of-life discards. They might actually not be discards at all. They might simply be what we call hibernating stock. So you might have, I would imagine that a lot of us have a cell phone or two that we don't currently use, but we didn't send in for recycling, right? So a lot of those might be those um, hibernating stocks, in addition to releases that are not, to the landfill that we don't recycle. If you subtract that out, what we have left circa 2015 is about 21% of what was mined is still in use today, more or less. And we can take those numbers and compare them, the flows out of use on any given year to primary production. So the flows out of use, something on the order of 1,200 metric tons. You subtract out those end of life, how much is actually being recycled or downcycled. We're left with something on the order of 800, maybe 900 metric tons, most of which again is in capacitors that could be recycled. If you compare that to primary production, for year 2015, if you recycle this quantity, that's more than the combined production of both the DRC and Rwanda. So you can completely shift away from that if you were to be able to recycle all this quantity. Of course, that is a tall order, and obviously economics needs to get a play in here, but we just wanted to get a ballpark estimate. Is this strategy even on the right order of magnitude, or is it simply, too small to even make a dent for tantalum? Okay, so that gives you a flavor of sort of the way we're thinking about it. I'll wrap up here and we can open it up to questions. I see that there's already several questions in the chat box, but just let me quickly summarize. So there's a combination of trends and issues that raise concern regarding the reliability of supplies. Most of these stem from the fact that production is becoming more and more concentrated in a few countries. It becomes doubly problematic if those countries are unable or unwilling to continue to supply to the United States. We've developed an enhanced methodology to help us identify which commodities are of greatest concern using a risk modeling framework. And there's a federal strategy out there that's an all-of-government approach to tackling this under these 6 calls to action that's currently being implemented. So I will stop there and get Betty and Susan maybe help me field some of the questions that are out there, and we can go from there.
Before you start, I did want to mention that we have the slides posted on our website, and we have been recording this session, and we'll have a recording available later in a few days. So with that, why don't we go ahead and answer some of these questions. Dr. Nedal, can you see the questions in the question and answer box?
I'm starting. So let's see. So Amy had a question. When you say share of elements produced in a country, is that just raw mineral or final product? Right. So that's a really good question. So when we looked at it, let me go back to one of those slides, especially for China. Here, what I have plotted here, I hope folks can still see it. For some of the commodities, we're able to get multiple supply chain stages. So for cobalt, for example, we looked at both mine production and refinery production. For some of the other commodities, we might only have one number. Now, specifically back to your question, is it material contained in the finished good? The answer is no. Typically, we're looking at primary production. And in fact, in this specific case, we're not even looking at total supply. We're just looking at primary production to the exclusion of secondary, so recycling. Good question, though. Okay. So let's see, the next question, I think from Anthony, when you are talking about countries where the elements are produced, it is clear to see that China is the predominant producer of these minerals. Please comment on the countries where the production is primarily controlled by China, for example. Okay, so the DRC cobalt example, right. So I'm not sure if this question came before or after I showed this slide, but obviously there is the issue that the previous slides that I showed were for domestic production of those commodities. So the Chinese slides were just looking at China's domestic production. In this case, obviously China has gone out or Chinese companies have gone out and made sure they have equity share in those assets overseas, especially in the case of cobalt. So you can see in this figure, Obviously, China has a very small share of cobalt mine production. They have a large share of refinery production. But if you include the Chinese companies' foreign ownership on an equity basis, it does become significant. And so yeah, you can look at that. And I think for most countries, uh, this is not an issue. There are a few that this is a significant issue, and China is one of those. Okay, Ben. So also, you're speaking to naturally occurring distributions to supply chains. Are you now considering things like the current COVID-19 pandemic? So we get this question a lot, right? So how is the pandemic really affecting supplies and supply disruptions? I think at this point it's too early to tell. I think it's obviously had an impact both on the supply and the demand, right? So on the demand side, you can imagine that demand for travel has decreased, right? So demand for aircraft have decreased as well, which means that things like um, the cobalt for the super alloys for the single crystal turbine blades has taken a hit, right? So on the demand side, also the demand for electric vehicles has somewhat softened a bit. It might come back quickly and strongly, but that demand has softened. So if we have softening of demand due to COVID-19. On the supply side, we've also seen some operations halt their production temporarily, either voluntarily or they're being told to do so. Some of those operations have restarted. We're also receiving reports that some operations are not able to receive, for example, the reagents that they need for their froth flotation, for example. In other cases, it's more about logistics, right? So are they able to get their material out of the country and to their customers? There are some reports from DRC suggesting that because of the shutdown, the 2-month-long lockdown in South Africa, some of the cobalt producers have had to find other ports. So typically, my understanding is that cobalt had to be shipped from Durban in South Africa to China. And so due to that lockdown, they've had to find alternative ports in Mozambique, for example, and Tanzania to get that commodity out to being refined in China. Now, in terms of our perspective, how are we going to address this? We're looking closely at all these trends. Once we have a clear picture of how, we're going to look at it in real term, but also once it's over, we can sort of look back at it and say, what have we learned? What did both suppliers and consumers, how did they get impacted? And we can use it as a lesson learned to be able to say, well, this is where, the impacts were really most. This is where companies were able to maybe find substitutes or maybe find alternative routes to be able to get the supplies they need. So it's really going to be informative for us to, I think, refine our model and tweak it on a real world scenario that happened, as we speak. Yeah, I think that's it. And if I'm only half answering your question, please chime in again. I'm happy to try to clarify some more, or maybe we can have a back and forth. But I'll keep going down the line. So I think Bill has the next question. So Bill, rare earth status of China ownership of Molycorp versus USA Rare Earths facility in Colorado. So I'm not really able to speak on individual operations per se. We try to be as neutral as possible. But yes, there is a Chinese ownership. I think it's slightly under 10% of the Mountain Pass mine. And I think it was deliberately under 10% to get under CFIUS, the Committee for Investment in Foreign Investment in the United States. I really can't speak much more about those issues or anything going on in that respect. So I apologize for that. I think I've answered most, if not all, the questions on the chat. Susan or Betty, are there any other things that you think I missed, or maybe others want to weigh in here? I'm not sure if we're going to open up the mics.
Can you open your chat box, Dr. Nassar? There is a a comment from Stephen Quinn.
Okay, let me check the chat box. Oh, okay, I didn't see those. Let me see. Okay, Stephen Quinn. One additional screen to consider is where there is no substitute. Yep, antimony, for example, has a very low economic factor, but regulation cannot manufacture do. Okay, absolutely. So yeah, so lack of substitution, I think is important. And I think in most cases, substitution is maybe overly optimistic that we're able to substitute our way out. I think in general, if there is a good substitute out there, it would have already been used, right? So there's a reason why this commodity is being used for this specific purpose, whether it's performance, whether it's economic, whether it's regulatory. These commodity, manufacturers are not going to use these commodities uh, without deliberately thinking about this. Um, and oftentimes, if there is a good substitute, they would have made that transition out. So for example, in multi-layer ceramic capacitors, most of those back in the 90s and before were based in palladium, right? But palladium obviously is a precious metal, and people didn't necessarily want to pay the high price, and the fact that it's concentrated its production in South Africa and Russia. So manufacturers were able to switch out to base metal, multi-layer ceramic capacitors. However, a significant portion of those capacitors still require palladium because those manufacturers are simply not willing to take the performance hit that would be required from switching from palladium to a base metal for that. So typically my sense is that if there's a good substitute, the substitution probably already happened. Substitutes can be developed. Typically it'll take, a considerable amount of time, 5 years or longer, probably more. And in some applications, the users are not willing to substitute out, whether it's for performance or, as you mentioned here, for regulatory purposes. So in the way we framed it thus far, we assume that in our time frame that we're talking about, which is the medium term, so we really can't look at things in the short term, like, in the next year or so. We really don't want to look at things in the super long term, so more than 10 years. And what our focus is really on is the next, several years to less than a decade, so maybe 5 to 10 years out. And in that time frame, I think you're right. And the way we view it is that substitution is probably, in most cases, is not a preferred option, and typically can't do very much for you in this medium term.
Okay, and I think someone was asking about the data. Is the data for this used for this presentation available for further research?
So a lot of this data is from our center, so the National Minerals Information Center at the U.S. Geological Survey. We publish everything that we can online. There's some things that we obviously can't publish if it's company proprietary. I think folks that know our data know that we have to sometimes withhold some of this information, and so that might be a concern. But typically our data are available. In some cases, we use other data sources, including, for example, the U.S. Census, which has the same attitude that we have, which is they provide everything that they can online. So if folks do have a specific data question, or if would like to have a piece of information, feel free to contact me, and I'll be happy to provide anything that I can.
And then we just had one last one come in from Stephen Riddle.
Yes.
Can you
So
see that?
Stephen's question, yes. Can you comment on the mineral graphite, since the listing supply is misleading, since I believe the critical issue with graphite is lack of production of the value-added graphite anode, both in the US and Europe for natural graphite as one source precursor. Yes, so I agree. So let me start maybe backing up here. We have to look at the commodity overall, right? So we have to look at its entire supply and its entire demand as much as we can. We try to get down to as granular a basis as we can, especially on the demand side. So what forms are being used and what applications those forms are being used in. In terms of graphite and natural graphite, Right. So the major concern there is the graphite that's going to be used for batteries, right? So it's spherical graphite that's made from natural graphite and to a lesser degree from synthetic. Um, so graphite is currently on the critical minerals list. We're revising the numbers now. I'm updating them to include synthetic graphite production and consumption. So it'll be a more holistic look at graphite. Um, I can't promise anything, but I don't think it'll be taken off the list. But in general, I think graphite is one of those that are on the top of the list because uh, of the lack of U.S. production of graphite in the United States. I'm not sure if that helped address your concerns about the way we're doing this or not.
Okay, well, that looks like about it. I'd like to thank Dr. Nassar and once again mention that we will have our the recording of this session on our website, which is the https://www.mmsa.net. The slides are already there, and we'll try to get a recording in soon. And thank you very much for everyone who attended. We'll be probably sending out a survey to you if you could fill that in and let us know what you thought. Thank you, everybody. Thank you, Dr. Nassar.
Thank you. Thank you for this opportunity.